This is Dr. Manjuna Chennapgod from Anveshana Academy, Bangalore, India. Dear students, in the previous class, we were discussing about Otto cycles and numericals on Otto cycle. Around 4 to 5 numericals we done on Otto cycle. Dear students, in the today class, I will move towards next numerical on Otto cycle. Numerical on Otto cycle. Fine. So I will move towards sixth problem on Otto cycle. First I will read the problem, then I will try to solve this numerical step by step. Okay. So an engine working on an Otto cycle has a volume of 0.45 meter cube, pressure 1 bar and temperature 30 degrees Celsius at the beginning of compression stroke. Okay, so at the end of the compression stroke, the pressure is 11 bar. Okay, then full stop. Then 210 kilojoules of heat is added at constant volume. Okay, now dear students, you have to understand very well here. Now he is telling Otto cycle in percentage, and he is also somewhere else he is telling that heat is added at constant volume. That means what we can say, it is a Otto cycle. Okay, so now he is asking to determine first one, pressures, temperatures, volumes at silent points in the cycle. First parameter. So second one, you need to calculate percentage clearance. Then next, efficiency of the cycle, net work per cycle. Next, mean effective pressure. Then last is ideal power developed by the engine if the number of working cycles per minute is 210. Okay, and you have to assume that the cycle is reversible. So these are all the data he has given. Dear students, so what you have to do, you have to first finding is what? You have to calculate the pressure, temperature and volume at all points of the cycle. Second one, percentage of clearance, that clearance volume percentage you need to calculate. Next, efficiency, work done per cycle, mean effective pressure, and you need to calculate the power. This is the problem he has given. Okay, now what all things he has given, try to understand the problem first thoroughly, then we will solve this numerical step by step. We will solve the numerical. So dear students, what all things he has given, that you can, I will try to mark here now. So what all things he has given now? Now an Otto cycle is there. Yes, it's an Otto cycle. He is going to supply petrol here. Otto cycle engine he has given. Otto engine he has given. It works on the principle of Otto cycle. Okay. So the related data he has given now. Okay, fine. So now he is telling that an Otto cycle volume of 0.5 meter cube, pressure and 1 bar, and temperature is 30 degrees Celsius at the beginning of compression. That means what? Beginning of compression means what? We can say this point is 1. Okay, this is point 1. Okay, this is point 2. Okay, it is what? Beginning of compression. So it is what? That means what? He has given pressure is 1 bar, volume is 0.45 meter cube he has given. You can see here. Next, he has given temperature, that is temperature is 30 degrees Celsius, that you can convert it into Kelvin by adding 273. That's fine. Pressure, he has given pressure, volume and temperature at 0.1. That means what? Beginning of compression. Now once it gets compressed, right? Once the piston reaches from BDC to TDC, then what happens? Whatever the air fuel mixture is there, right? That will be get compressed. Once it's compressed, then what happens? The pressure is going to increase. That pressure, increase in pressure, that point 2, when piston reaches at point 2, that we can call it as a point 2. The pressure at point 2 we can mark it as a P2. Then volume I will mark it as a V2. Then temperature I will mark it as a T2. Now when it gets compressed, right, the pressure is increased from 1 bar to 11 bar. That means what? P2 he has given, but he is not at all given V2 and he is not at all given T2, but that we can determine with the help of a Otto cycle. Okay, with the help of Otto cycle I can determine all these. Okay, fine. Now next, okay, now is once it gets compressed, right, once the compression is ends, then what happens after at the end of the compression process, what he will do is going to supply certain amount of heat. That amount of heat I will mark it here as a QS. That he has given the amount of heat supplied is, that data is already given in the problem, that is 210 kilojoules of heat is going to supply. Once the heat is supplied, what will happen now? The piston will start to move from TDC to BDC. That means what? Expansion will take place. That too, during expansion there is no heat transfer at all. That means what? Q is not at all taking transferred from system to the surrounding. That means what? Adiabatic process or adiabatic expansion process, we can tell. This is a given data which is related to Otto engine now. Okay, so now I will try to draw the PV diagram and I will try to understand the problem with respect to PV diagram also. That you can see here now, dear students. When it is at point 1, right? When it is at point 1, that means what? Beginning of compression. This you already know. It is what? Compression process. That to adiabatic compression process. Beginning of compression, that to point 1. He has given P1, T1 and V1. So that is nothing but what? At point 1, P1, 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 T1, V1 he has given. That's fine. The next, once the air fuel mixture gets compressed, that means what? Piston reaches at point 2. You can see piston reaches at point 2. That means what? The pressure is increased. How much pressure is increased? That is 11 bar. That is nothing but what? P2. So P2 increases to, that is P2 is 11 bar. Then what you will do? Once a compression gets end, right? That means what? At the end of the compression, what he will do? He is going to supply certain amount of heat. That amount of heat he has already given, that is 210 kilojoules. Once heat is added, right, what happens now? Pressure also increases, temperature also increases, and increases. That increase in pressure and temperature we can mark it as a 0.3. Then pressure at 0.3 I can mark it as a P3. The temperature at 0.3 I will mark it as a T3. That means what? These two are maximum conditions. That means what? Maximum pressure, maximum temperature. So these are the maximum condition. Once what happens now? Because of the sudden explosive force which is created by the hot gases, then what happens? The piston will start to move from 3 to 4. That means what? We can call it as expansion. In the expansion there is no heat transfer at all. That process we can call it as a adiabatic expansion. Then it is going to reach from again TDC to BDC. Now, so once it expansion start, right, then what I can do now? I can mark it here, point 3 to 4. Okay, 3 to 4. Now piston will start to move from 3 to 4. Once the piston move from 3 to 4, what? Expansion will takes place. The temperature at expansion I can mark it as a T4. Pressure I can mark it as a P4. Okay, once it's end, right, then once it expands, right, that what we will do? We are going to open the exhaust valve. Hence what happens? Heat is going to reject. That heat rejection is represented as a QR. With help of this QS and QR, what I can do? I can calculate the work done. Once you know the work done and heat supplied, you can calculate the efficiency also, dear students. Okay, that's also very important here now. So that's what the Otto cycle help us to analyze the performance of the engine. That is the contribution which is given by the Otto. Okay, this is what problem which is related to the values. Okay, then V1 also he has given, that is 0.45. That means what? Total volume from cylinder head to BDC is what? V1 we can say. That means what? Total volume we can call. Again, when it comes to volume, swept volume will come, clearance volume will come, total volume will come. Okay, but he has given total volume, that is V1. Okay, fine. Now, so what I can do now? You understood the problem, right? Now try to list out the given data here now. So what is that? V1 0.45 metric cube he has given. P1 he has given 1 bar. Temperature he has given 30 degrees Celsius. I will convert that 30 degrees Celsius into Kelvin by adding 273. So therefore 303 Kelvin is the inlet temperature before compression. Okay, once the compression takes place, right, the pressure of the air is going to change. That means it is going to increase, that is 11 bar. P2 is equal to 11 bar. Once it gets compressed, right, he is going to supply certain amount of heat. That amount of heat supplied is represented as a QS, that is equal to 210 kilojoules. These all data he has given. But first thing what he is asking now, the first finding is what? He is asking to calculate is asking to calculate what is the pressure, temperature and volume at all points. Silent points means what? Wherever the all points will come, right? 1 2 3 4 like that, you can see here now. Just a minute. Okay, is asking to calculate T1, T2, T3, T4, like P1, P2, P3, P4, like that, V1, V2, V3, V4, that he is asking. But some data he has given, V1, T1, P1 he has already given in the problem. So we need to calculate the other temperature, pressures and volume. How to solve that? That we will see here now, dear students. Okay, to calculate that, now to calculate the pressure, what I will do, I will go with adiabatic compression. That is what first process, 1 to 2, 1 to adiabatic compression. We are having an equation, that is P1 V1 to the power of gamma is equal to P2 V2 to the power of gamma. This ratio we are having now. Now what I will do, I will try to calculate the P2 value with help of this equation, because P2 is not at all given, that I can calculate. How to that I will calculate, we will see that. Okay, so now in quick, what all things he has given now. Okay, so now we'll try to understand the problem in short. Okay, so now what all things, the given problem is Otto cycle. Then the first process is adiabatic compression. With help of adiabatic compression, what we can do, we can calculate the compression ratio. With help of temperature ratio, I can calculate the T2 also. Okay, this is what adiabatic compression, that is the starting first process. Then what will happens now, during adiabatic process, what will happens, pressure is going to change from P1 to P2. With help of this, what I can do, I can calculate the P2 also. Okay, then temperature also I can calculate, as it is with help of temperature ratio I can calculate T2 also. This is what adiabatic process. Now once the compression is ends, then what we are doing, we are going to supply certain amount of heat at constant volume. Now that means what, constant volume process will come. With help of that compression constant volume, we can use the pressure ratio equation, and we can, okay, so that is what constant volume. Okay, heat is added. Now we are going to add heat at constant volume, that is nothing but heat addition. So that heat addition, I can write the equation, that is what, Qs is equal to m into Cv into T3 minus T1. Okay, fine. So once heat is supplied, then what happens, the power is going to generate inside the cylinder. That means what, power developed. With help of work done equation, okay, I can calculate the power develop with help of a work done equation. Okay, this is about what, power development. Okay, when the piston is moved from BDC to TDC, there we are going to get a clearance volume and total volume. With help of clearance and total volume, what I can do, I can calculate the percentage of clearance. Okay, with help of shaft volume and clearance volume, what I can do, I can calculate the percentage of clearance. Okay, once it done, what I can do, I can calculate the efficiency of the Otto cycle with the help of a heat rejection equation. What is the heat rejection equation? With that also we know, the again heat rejection is taking place at constant volume, that is m into Cv into T4 minus T1. This is what the problem. Okay, with help of that, what I can do, I can calculate the heat rejection. How to solve this numerical? Step by step I will solve it now. Okay, the first one, with help of pressure ratio, dear students, P2 by P1 we know already. During adiabatic compression process, the pressure ratios can be written as P2 by P1 is equal to V1 by V2 to the power of gamma. Or else what I can do now, R equal to P2 by P1 to the power of what, gamma to the power of 1 divided by gamma. Okay, what is R here now? Already I told in the previous class, dear students, R is equal to what? That is the compression ratio, that is nothing but what, V1 by V2. Wherever V1 is there, right, I will take R, then I will take R outside, then it will come at right side, that means what, 1 divided by 1 to the power of gamma. So then what I will do, I will try to substitute the value here now. So therefore R equal to, I don't know the value of R, I will keep it as it is now. R equal to, what I will do here now, P2 by P1. What is P2? P2 he has already given, that is 11 bar. Then P1 also he has given, that is 1 bar to the power of what, 1 divided by gamma, that is constant. Then do simplification, you are going to get, that is R equal to 5.5. that is 5.5. That is nothing but what? Compression ratio. As I told dear students, there is no unit for compression ratio. Why it's so? Because if it is V1 is in meter cube example, then V2 is in meter cube, then what will happen? Meter cube will get cancelled. Hence there is no unit for the compression ratio. Now compression ratio, that is R equal to 5.5. I got this value. I will keep it aside. Now again, what I can do, the variation of temperature versus volume during adiabatic compression, that can be expressed in terms of temperature and volume, like T2 by T1 is equal to V1 by V2 to the power of what? Gamma minus 1. So dear students, you can see here now, I need to calculate the value of T2 because T1 he has given, but V1 by V2, that is compression ratio, that is R, that you already calculated, that is 5.5. Then gamma, you know, that is 1.4, that is a constant for air. Then you can easily calculate the T2. So then what I will do now, I will modify this equation. This is nothing but what? R. I will write it R to the power of what? Gamma minus 1. Now what is the value of R? That is 5.5 to the power of what? Gamma value 1.4 minus 1, then what you will get now? Now you will get the do simplification, you are going to get 1.977, or you can mark it as a 1.92. So therefore what you can do now? So therefore what you got it here now, T2 by T1 is equal to how much you got? 1.98 you got it now. So then if I want to calculate T2, then what I can do now? I will take T1 this side. So therefore T1 into 1.98. So therefore, T2 is equal to T1 into 1.98. But what is the value of T1? T1 is given in the problem itself, that is 30 degrees Celsius. I mean that is 30 degrees Celsius, nothing but what? 303 Kelvin multiplied with what? 1.98. Then you are going to get 600 Kelvin. So therefore what you can do? T2 is equal to 600 Kelvin. Okay, fine. Now applying gas light 0.192, that means what? Again adiabatic compression process. I will apply now P1 by V1 because it's a constant volume process. P1 V1 divided by T1 is equal to P2 V2 divided by T2. Now what is the V2 value? So I will try to take the value of V2 here now from this equation, because I don't know the value of V2. The only we know already P1, V1 we know, T1 we know, but P2 we already calculated, T2 also we have calculated, but we don't know the value of V2. That I can calculate here now. I will modify this equation. Then I will try to take the value of V2 outside. So therefore V2 is equal to T2 by T1 into P1 by P2 into V1. Okay, so V2 is equal to, so now P1 by P2, this one, then V1 by V2, sorry, T1 by T2, the next into multiplied with what? V1, then T2, V2 I will take it outside. So therefore what I can do here now? So what is T2 by T1? So that is what? 600, you can say 600 divided by 303. Okay, then next multiply with what? P1 is equal to 1 bar divided by P2. The next multiplied with what? 0.45. Dear students, do simplification. You are going to get V2 value, that is equal to 0.081 meter cube. That is V2. Fine. Now once the compression process gets over, then what we are doing now? We are going to supply certain amount of heat. That heat is represented as a QS. That heat, I can write the heat supplied equation as QS is equal to M into CV into T3 minus T2. Dear students, but QS he has already given in the problem itself, that is equal to how much he has given? 210 kilojoules he has given. Then M is equal to, we are calculating heat supplied per kg of air, that is equal to what we can say? We can say unit mass, that is 1 kg. Then CV is the specific heat of the air at constant volume. Then T3 we don't know, I will keep it as it is, but T2 I already calculated here, that is 600 Kelvin. Then only unknown is what here now? Dear students, we can see here now, only unknown in this equation is T3. I will modify this equation and I will rewrite this equation. So like that we can see here now. So that is nothing but what? 210, heat supplied is 210. The next M is equal to 1 again, CV is equal to 0.517 into, sorry, he has given mass is equal to something else. He has given that mass, how to calculate that mass, but in this problem he is not telling, mass, calculate the per unit. He is not at all asking for unit mass, but he is asking to calculate some mass. That mass I can calculate with the help of what? Ideal gas equation. Okay, that is what m is equal to P1 V1 divided by R into TV, because we know already PV m RT. So it is the equation. With help of this, what I can do, I can calculate the m value. So that m value we have calculated, that is 0.517 kg. The amount of air which is supplied in the cylinder, that is equal to 0.517 kg. Hence, what I can do now, with help of this data, I can calculate the heat supplied. So therefore, Qs is 210, m is equal to 0.517, Cv is equal to 0.71. The next T3 we don't know, I will keep it as it is, but T2 we have already calculated, that is 600 Kelvin. I will do simplification. Then what I will do now, I will get the value of what? T3. I will get the value of what? T3. How much is T3? That we will see it now. Okay, so now you can calculate that. So what you can do now, with help of this, with the help of PV diagram and pressure ratio equation and temperature ratio equations, you have calculated P2, T2, next P3, T3 you have already calculated, but T3, how much is T3? That you can simplify and we can get the answer T3. Similarly, what I have to do then, I need to calculate T4 and P4. So how many processes are there now? 1 to 2 is what? Adiabatic compression. Then next 2 to 3 is what? Heat addition at constant volume. Then 3 to 4 is constant adiabatic expansion. The next 4 to 1 is what? Heat rejection. That is what? QR. So Q heat loss, heat supplied. Okay, this is the things now. With the help of these all processes, what I can do, I can calculate the temperatures. Now do simplification, dear students. I will do simplification and I will try to take the value of T3. That T3 I am going to get 1172 Kelvin. Dear students, just you can have a comparison where T2 you got 600 Kelvin, but you got T3 is equal to 1000, almost double. Why so? Because we are going to add heat at a constant volume, that too from 2 to 3. Because of that heat addition, what happens? There is a sudden rise in the temperature. Hence, T3 is the maximum temperature, that is around 1200 Kelvin. Okay, fine. Now, what I will do now? I will move towards next 2 to 3 process, constant heat addition. That is nothing but what? P3 by T3 is equal to P2 by T2. I know the value of what? T3. Okay, P2 I already calculated, but the only unknown is what? P3. So then what I will do now? I will I will modify this equation and I will try to take the value of P3. So therefore P3 is equal to T3 by T2 into P2. What is T3? That you already calculated, 1172 Kelvin, divided by T2, that is 600 Kelvin, multiplied with P2, that is 11 bar. Do simplification, we are going to get the value of P3, that P3 is equal to 21.48 bar. So you have calculated P3 also. How much it is? 21.48 bar. Okay, dear students, we should not forget one condition. What is that condition? We know already. We know at constant heat process, you can see here now. What is that? V2 is equal to V3 and V1 is equal to V4. If you calculated V2 value, that is nothing but what? V3. If you calculated the value of V1, that is nothing but what? V4. The same thing you can see here now. So therefore, V2 we already calculated, right? That is nothing but 0.081. That is nothing but what? V3. So V2, V3 also done. But what I am doing here now, dear students, I am going to calculate pressure, volume and temperature at all points. P1 he has given, T1 he has given, V1 he has given. I calculated P2, T2 and V2. I have calculated P3, T3 and V3, and also I am calculating P4, T4 and V4. So now what is V4? So V3 is equal to V2, these are 2, V1 is equal to V4. So according to the Otto cycle. So therefore what I can do here now, adiabatic isentropic, then I will go with what? Next one process. Just a minute. I will go with process 3 to 4. 3 to 4 means what? Adiabatic expansion. There we are having a condition now. P3 V3 to the power of gamma is equal to P4 V4 to the power of gamma. But I don't know the value of P4. That P4 I can calculate with the help of this equation. I will modify this equation as P4 is equal to P3 into V3 by V4 to the power of gamma is equal to what? What I can do? P3 Okay, P3. What is V3 by V4? That is what? Expansion ratio. But V4 by V3 is expansion ratio. But here it is a V3 by V4. That what I can do now? I will make it as a 1 divided by R actually. So to the power of what? Gamma. Do simplification. You are going to get the value of what? P4 as 1.97 bar. Dear students, we can compare P3 and P2, P3 and P4 also, because P3 and T3 are the maximum pressure and temperature. That we can see here now. What is the value of P3? Dear students, we can see here now. P3 is maximum 21.48 bar, but here it is almost 2 bar. There is very less pressure. Okay. Now, and also we know the value of we don't know the value of T4 also. That also we can calculate here now. What is T4 by T3 is equal to? We have the equation. Dear students, we have to follow V3 by V4 to the power of what? Gamma minus 1. So therefore, do simplification. T4 by T3 is equal to 1 divided by R to the power of gamma minus 1. 1 divided by, okay, R value we already calculated, right? Compression ratio. That compression, as I told, R, that is compression ratio, right? That compression ratio is equal to what? Expansion ratio. Compression ratio is equal to expansion ratio, that is equal to R, that is equal to, we have already calculated 5.5. Then to the power of what? Gamma 1.4 minus 1. You do simplification, we are going to get T4 by T3 is equal to 0.505. Then take the value of T4 out. The T4 is equal to 0.505 into T3. What is the value of T3? T3 we know already. That is how much? 1172 Kelvin. Do multiply this 0.50 with that 1172. Then what we will get? You are going to get the value of T4 is equal to 591.8 Kelvin. Again, dear students, you can see the T4 is 591, but whereas T3 is 1172 degrees Celsius. That means what? T3 is the highest temperature or maximum temperature in the cycle. Now I have calculated the T4. But dear students, I don't know the value of V4 also, right? That V4 we know already. V4 is equal to V1. That you can see now V1 is equal to V4. So that means I have calculated all the values, pressure values, temperature values in all points. Point 1, 2, 3, 4. Okay, fine. This is what our first finding. Once it done, then what is our second finding? Second finding is I need to calculate percentage of clearance. What is percentage of clearance, dear students? You can see here now. Just a minute. Okay, so percentage of clearance. That means what he is telling, VC, percentage of clearance is equal to VC divided by VT. That is the total volume. Total volume means what, dear students? We can take the volume from this to this. That is something about what? VT. That we can call it as total volume, or we can call it as a V1 also. So V1 is equal to, when the piston is at point, right, that volume, whatever the volume which is occupied by gas is V1, that is nothing but what? Our total volume. Okay, once the piston when the piston is reaches TDC, the air fuel mixture gets compressed. That volume we can call this volume, only this volume. Assume that if the piston reaches TDC, we are going to get one more volume. That means when air fuel mixture gets compressed, that volume I can call it as a compression volume, or we can call it as a V2 volume. So if I want to calculate the percentage of clearance, is nothing but what? It's the ratio of clearance volume to the total volume. So therefore what I can write now? VC divided by V1 also I can write it now. The same formula I have written it here now. Okay, so VC by VS. What is VS here now? Swept volume, dear students. Sorry. Percentage clearance is the formula is, just a minute, sorry. VS divided by VS, not V1, VT, dear students. But what is VS here now? VS we already know. Total volume minus clearance volume. That means what? Volume between just a minute. Okay, so percentage of clearance is equal to VC divided by VS, dear students. VC is nothing but what? This is the volume, is nothing but what? Clearance volume, or VC. but the volume between BDC to TDC is nothing but what? Swept volume, dear students. Now swept volume, okay, swept volume. But here it is a V1 and here it is a V2. So what I can do now, if I want to calculate the value of swept volume, what I can do now? Swept volume is nothing but what? Total volume minus this. Now that is nothing but what? V1 minus V2. What is V2 here now? Just you can see, if it is the point is at this, right, whatever the volume is, right, that we can call it as clearance. That is nothing but what? V2. So if I want to calculate the swept volume is nothing but what? Total volume minus this much, V1 minus V2. That is nothing but what? Swept volume. That's what I am taking here now. Okay, so VC divided by Vs. So Vc is nothing but again V2, that is our clearance volume. So Vc is equal to V2. So V2 divided by swept volume is nothing but what? V1 minus V2 multiplied with what? 100. V2 we know already. V1 he has given in the problem itself. Do simplification. Then we are going to get percentage clearance is 21.95%. This is our second finding. Next I will move towards next efficiency. How to calculate the efficiency? We are having an equation. Okay, what is that equation? To calculate efficiency, we are having an equation. Otto cycle, efficiency of Otto cycle is equal to what? We know already. Efficiency is nothing but what? Work done to heat supplied. What is work done? Work done is nothing but what? That also I told, right? Work done is equal to QS minus QR. Okay, so therefore how to calculate QS? And QS he already given in the problem, but we don't know the value of QR. That we can calculate with the help of a basic equation. What is that? QR is equal to M into CV into T4 minus T1. But dear students, here I am not taking M is equal to 1 kg per kg. I am not calculating, but how much amount of air you have supplied, that quantity I am going to consider here now. So therefore what I can do now? QR is equal to, how we can solve this problem? Just a minute. So QR is equal to M is 0.517, that we have already calculated with the help of ideal gas equation. Then CV is 0.71, T4 we know already, T1 also he has given in the problem. Do simplification. You are going to do simplify or calculate. Then you are going to get the value of what? QR is equal to 106. Now dear students, you know the value of QR and QS. What we can do? We can easily calculate the efficiency of the Otto cycle. So efficiency of the Otto cycle is nothing but work done divided by heat supply, where work done is equal to what? QS minus QR divided by QS. So what is QS? It is given in the problem itself. What is QR? That we already calculated. Then do simplification. You are going to get efficiency of the Otto cycle is 49.5%. This is what general equation. Efficiency is equal to work done, heat supplied. But this efficiency I can calculate with the help of the standard derived equation of Otto cycle. What is that equation? We know already. This equation we have derived, right? That efficiency I can calculate in another way also. How it is, that you can see now. Efficiency of Otto cycle is equal to 1 minus 1 divided by R to the 4 of gamma minus 1. This is a standard equation. This is a derived equation. Then I will substitute all the values. 1 minus R 5.5 to the 4 of 1.4 minus 1. Do simplification. You are going to get 49.5%. Both are same. I have done we can calculate efficiency of the Otto cycle in any other method. Okay, in out of these two, we can use any method to calculate the efficiency of the Otto cycle. Now third parameter is done. Next, what is the fourth parameter? Fourth parameter is, that is mean effective pressure. Mean effective pressure, some authors they will write MEP, some authors they will take PM. So here we will take PM. Okay, what is PM? We have done already in the previous class. PM is equal to, that is mean effective pressure is equal to, it is the ratio of work done to the swept volume. What is swept volume? That also I told dear students, that we can calculate as V1 minus V2, or else with the help of bore diameter also we can calculate swept volume, that is pi by 4 into d square into L. But here we can calculate swept volume with the help of V1 and V2. So therefore what I can do now? What is work done? What I told now, work done is equal to, we already told, right? So work done equal to QS minus QR. That I already told, right? So QS we know. I will substitute QR. I will substitute V1 and V2. I will substitute. Then do simplification. You are going to get them 2.81 bar. So dear students, kilojoules is the right heat supplied 210 here. Kilojoules is the right. I will convert it into joules now by multiplying 10 to the 4 of 3. Okay, then we can convert that dividing by multiplying that, we will get it in terms of what, Newton meter. But if you want to convert it into bar, then what I can do now, I have to multiply with what, 10 to the power of 5. So I am multiplying 10 to the power of 5. Then what you will get now, mean effective pressure. That means what, the mean effective pressure on the piston is equal to how much, that is 2.81 bar. That is what our fourth finding. Yes, we calculated the mean effective pressure. Next, power developed. Now if the pressure, if this much amount of mean effective pressure acting on the surface of the piston, then how much power is generated at the crankshaft, that we can calculate. To calculate that, we are having an equation now. So power is equal to work done per second. That how we can calculate, work done per cycle into number of cycles. But how many cycles are there, he has given some cycles also. How many cycles he has given, 210 cycles he has given. Okay, how to calculate the work done, that is qs minus qr, that is work done multiplied with what, how many cycles, 210 cycle per second is given. So we have to put answer in terms of per seconds. Okay, but that you can see, dear students, I will come back to the problem that you can see here now. So number of cycles, how much he has given, number of cycles he has given 210 per minute he has given. What you have to do, you have to convert it into per second, because joules per second is what, always we know 1 watt. Hence he has given, when he has given the value number of cycles per minute, the 210 per minutes, that we need to convert it into seconds. So that's what I'm converting here now. That's what I'm converting here, dividing by 60. Hence what you will get, you will get kilojoules, joules per joules per second. Joules per second is nothing but what, watt actually. So how much you will get, 364 kilowatt power watt you are going to get, 364 kilowatt. So therefore what we can do, final answer, that is power developed by the piston is, or power developed by the engine is 364 kilowatt. Dear students, this is how to solve the problem. Dear students, I hope you understand the problem well. Okay, if you have any doubt, you can ask me in the comment box. Okay, dear students, here I request you, please subscribe my channel, like and comment. Please support me. Thank you.